Thank you much, and thanks everybody for coming. I'm very happy to be here. I'm very happy to be back to Georgia Tech. I'm going to tell you about my ideas and ideas we have been working on with Max, Santos, and others on biologically plausible intelligence in several important ways. I'm just reading from, natural language, not, interpretation, finding the true meaning of language and basically communicating and decoding the meaning of communications, of interactions, linguistic interactions, common sense reasoning, understanding the world, invention and ingenuity, continual learning, understanding emotions of others, understanding society. It's not biologically plausible. Okay, this is another flaw that it's intelligence, but it's artificial intelligence. Okay, so by the way, how do I know all this? I know it. I found out the old-fashioned tough cop way. Okay, I interrogated AI until it confessed. Okay, so this is output from ChatGPT from a couple of weeks ago. So, all right. For everybody, this is a challenge, right? So how this is a lot of stuff that AI still cannot do, and the question is, how do we fix this? Okay, and where do we start? Natural language is a very attractive option because that's where actually the most acceleration has happened in the past years. For me, this is an important the fact that learning, artificial learning, cannot be adaptable and continual. Okay, so we are good at keeping learning all our lives, but I believe that the clever thing to do here is to go to the root, okay? Because in some sense, the last bullet is not a defect, but it's an overarching reason, okay? Obviously, AI is behind brains because AI systems are not brains, okay? They are something else. They are not biologically plausible. They don't. So this is the challenge. This is what we have been trying, and this, of course, brings us. It's the long haul. This is the hard bullet to attack. Okay. Why? Because you have to start AI from the beginning, number one, and number two, you have to understand neuroscience. Okay, and if you, that brings us to our common interest. Neuroscience has its own little hiccups, its own little obstacles. Okay, we are all after this overarching question: how does the brain create the mind? And obviously, we are not very close to answering because there are, here are the two books that we know very well, standard textbooks in cognitive neuroscience and experimental neuroscience. And essentially, these are two great works of science that don't reference each other. Okay, so they're very far. There is a huge gap between the students of the brain and the students of the mind. And this gap is not only scale, 10 to the 11 is a big number, but also is a gap in experimental subjects, of course, but also point of view, methodology, mindset. Okay, Richard Axel recently put this, not so recently anymore, okay, put this in writing when he said that what we are missing is a logic for the transformation of neural activity into thought. I view discerning this logic as the major open question in neuroscience today. So, I mean, when Santos and I read this, we thought that we were blessed by the Pope. Okay, because this is sort of what we have been after. Okay, trying to bridge this gap. Okay, and the question is, here are two surprises in this statement. Okay, one is that Axel, who is the most dedicated fanatical empiricist that I know, uses the word logic, which to my mind means formal system, which is ultimately computational. The second surprise is that only Santos and I are working on this. Okay, so we don't. I'm not aware of many people trying to do this bridging. Okay, cool. So here is what I'm going to show you. It's our approach. We define a mathematical model of the brain. Yes, you read correctly. A mathematical model of the brain. Okay, yeah, and it's such that it models reasonably well spiky neurons and synapses. It does not model accurately. It captures the essence of, in other words, it really addresses a little bit the criticism of biological implausibility. And that this system is able to implement cognitive phenomena. Okay, so, and I'm going to describe it to you. Is this clear? Okay, so I'm going to start by describing to you a mathematical model of the brain. And basically, it is a finite number of brain areas. And we assume that each has n excitatory neurons. Think of n as 10 million. These areas are also connected by fibers of random connections. Okay, that there are some pairs of areas are connected this way. Okay, that there are random connections between any neuron up there and down there, and all areas are recurrently connected in a random way. Okay, by random we have the simplest kind of random graph, which is the GNP, the Herder-Sereny graph. Any two neurons have the same probability of, any pair of neurons has a probability P of having a connection from the first to the second. And we know that the brain is not wired like that, but we have used different models of random connections, and we get, and the behavior seems to be robust. So we assume that neurons fire in discrete steps, which we all know doesn't happen, but we don't think that that's a distortive assumption. So here is a major assumption that at each step in each area, k, a small number out of n neurons fire, and in fact this particular k that have the highest synaptic input from the previous step. Okay, and this of course models local inhibition. So this is well, getting close to a full description of the model. Also, an area can be inhibited or during a step, or disinhibited, of course, the next step. Finally, plasticity. And we have very simple Hebbian plasticity that if two connected neurons fire together, in other words, the presynaptic neuron fires and the postsynaptic neuron fires the next time step, then the weight of their synapses multiplied is increased, let's say, by 5%. So in many ways, the only things we model with this model is plasticity, randomness, and selection. If you think about it, these are the three main forces of life. And typical parameters, you can think of as, n is perhaps 1 million or a dozen million. K is roughly the square root of that. P is 100 or 1,000, and that's the probability that two neurons are connected. And beta is 5% or thereabouts. Okay, so this is the model. This is the parameters, the range of parameters, and in fact, okay. So there are some details that I'm not mentioning that are not very crucial. And the point is that this defines a dynamical system. The state is the neurons that spike and the synaptic weights and the inhibited areas. Okay, and the next step function is well defined now. And it turns out that you can run this system, and what you notice that an emergent behavior, a very strong, robust emergent behavior, is what we call assemblies of neurons, what everybody calls assemblies of neurons, which is representations of outside world objects through or ideas through a subset of the neurons in an area. And by the way, are there any questions? Am I losing many people?
I missed what P was.
Sorry, P is the is an important parameter, which is how dense the synaptic network is. What's the probability that if I take two random neurons, they are connected by a synapse? And we assume that that's uniform. In other words, that doesn't change. And we know that the brain is not like that, but sort of, using more sophisticated models that try to imitate the brain better does not change much the behavior that I'm describing. Thanks. Anything else?
How important is the partitioning to brain areas, or do you have certain?
Yeah, very. And assume that it's rigid, okay? And I'm aware that this is not always sort of warranted. Okay, yes. It is very important. Yeah. In other words, we need many areas for things to work for us. Okay. Okay. By the way, the simulator of this is available online. Okay, so it's in fact in order to start it, you have to type in your monitor load brain, which is a great thing to do at 6 o'clock in the morning. By the way, at this point, I get the question how is computation initiated, and typically by external stimuli. Okay, so we have a similar way of modeling external stimuli and input data. Okay, and assemblies of neurons are sort of the soul of this. Okay, and as I told you, it's an emergent behavior of this simple mathematical model, and I'm sure that you are familiar with what they are, but they have dreamed them in 1949. Neuroscientists have been trying to find them in the brain for a long time until technology became good enough. So, Busaki's group, Ken Harris, were the first to measure it. Many others, and by now, many people study them, create them, manipulate them, excite them, and so on. So it's a well-established feature of brains, and one that many people believe that is very important for the way the brain works and how it creates the mind. Busaki, for example, Yuri Busaki at NYU, his recent popular book, he calls them the alphabet of the brain. Okay, that this is, which is a very wise term, because I think the assemblies are where sort of sub-symbolic computation starts to become symbolic. Now, assemblies have some interesting behaviors, okay, which we have been studying for many years. I'm listing here on the left assembly projection. So it means that if you have a representation in assembly in one area, and the setup is right, there is, for example, afferent synaptic connectivity from an area to another area, then this assembly, by sort of firing for a few times, can create a copy on the other area. And this copy is sort of a stable copy. It's a new assembly, but also it has the property that every time this assembly fires, this will fire also. Okay, and there is something called a reciprocal projection, which basically goes the other way. Wherever the copy fires, the original also fires. Okay, so there are association. Okay, association is the following: that if you have two stimuli, okay, for example, my brother and the pyramids, and they have created assemblies in my brain, and I find out that my brother is at the pyramids right now. Okay, so these assemblies are going to change a little so that they intersect more. Okay, that there is association. Pattern completions. The assemblies are sort of stable enough so that if you ignite 5% of them, of each one of them, the rest is going to sort of 99% is going to fire. Merge, okay, that you can create if you have two assemblies in two areas. You can create an assembly in a third area that essentially can represent these assemblies. This is how you can build trees in the brain. Okay. Sequence recall, an important property of assemblies that we discovered recently. That basically, if you have three stimuli, okay, and you project them into the brain in particular sequence, then if one of these new assemblies fires, the sequence will complete itself very robustly. Okay, so assemblies have an interesting way of remembering their order. Okay, and through, of course, synaptic plasticity, sort of latent synaptic plasticity. And this has many other. You can basically teach a brain to act like any finite machine. Okay, so you can do things like that. And also few-shot learning of simple classification tasks. So basically, if you of course, you can if you have a stimulus, you can memorize it. Okay, our hippocampus does this all the time, several times every second. But here's the point: that if you have a class of stimuli, for example, the face of somebody that have some through, of course, a lot of processing by the visual cortex, that have a lot of intersection that are almost the same, except for that have a lot of overlap between them. Then you can learn this class of stimuli, and in the future recognize this person, even if this person comes in an angle that you see this person from an angle that you have never seen them before. Okay, so all these are behaviors of assemblies, and sort of a lot of our work with Santos, Max, Mirabel, so is trying to prove theorems that convince you that these will happen with high probability. With high probability, you realize is necessary because the whole basis of this is a probabilistic connectome, okay, a random connectome, okay. And if it is random, with some astronomically small probability, this random connectome has no synapses whatsoever, okay. So you have to say with high probability because otherwise it's not a valid theorem. Is this clear what I'm saying? Or yeah, okay.
Are assemblies synonymous with brain regions, or each
No, no,
brain
no, no,
region
no.
has multiple?
Oh, no, no. Each brain region has multiple assemblies. Actually, I'm going to talk about a brain region that has 100,000 assemblies in your brain right now. Okay, that's the lexicon. Okay, you know, where your knowledge of words resides. Yeah. So yes, and they can overlap, of course. They can overlap by chance. They can overlap deliberately, encoding some semantic connection and so on. Yes.
Similar as a single assembly limited to one area.
Yes. And we'll talk about that. Yeah, it's a great question. Yes, but we'll revise that. Thank you. Any more questions? Yeah.
Is the connection probability you're using for the for the recurrent connections within an assembly or inter-area connections the same or the same?
Yeah, so it's just random connections that any two, either in the same area or in the two different areas, they have the same probability of being connected. Okay, so it's the simplest possible model. Its magic is that you can prove theorems using it. And then you can say, okay, what if it's a little more complicated? And you see that the same behaviors emerge anyway, so you stop worrying. Okay. There is one part of my narrative that I left unexplained. I told you that some areas can be inhibited and disinhibited, okay, from time to time. And how is this done? And here is sort of, I promise, the last sort of element of our model, which is long-range interneurons, okay? So these are long-range interneurons. I learned them from Yuri Buzaki, from his work. And we know they exist, okay? So we know, and they get heavy use in our model, okay? One criticism to our model, so we know that, for example, Peter Dayan recently told me spoke his mind to me that what we call long-range interneurons, there are other mechanisms in the brain that could replace them, like thalamocortical striatum control loops. Okay, so we know that they have similar effect, but sort of we have here sort of think of it as a to fix ideas. This mechanism of long-range interneurons. Let me tell you how they work. They are the green areas, and they have the following property that they can inhibit either other areas or other populations of long-range interneurons. Okay, and they can have synaptic inputs. They can tie together with areas, with particular assemblies in areas. Okay, and this is what this arrow says. In other words, they can be recruited by areas and assemblies so that they can do their work, their remote work. Okay, inhibit and disinhibit remote areas. And these are the control of, these are sort of, the program of our system. Okay, so the computational system I present to you is essentially a hardware language, programming language, and you know all of these components right now. Okay, so you can set one of these up, and then wait for stimuli. Okay, and see what happens. Okay, that's the idea. Yeah.
Are these long-range neurons recruited? So they're recruited by specific assemblies. Do they target specific assemblies?
No, they target whole areas. And typically they're recruited by all the relevant assemblies in an area. Okay, so yes.
So any spontaneous activity in your networks?
Not in mine. Okay, you are right. You are, one spontaneous activity is that we have some kind of homeostasis. Okay, so we know that, but we don't. We have not sort of, by the way, I'm not sure about the answer to your question. So, you tell me if any of what I'm going to tell you is spontaneous or not, okay? Qualifies for spontaneous. Okay, so what I'm telling you is that if you put together LRIs and assemblies, or and the other, the whole model that I showed you, these together they give you all of computation. Okay, so we have proved that, remember, n is a huge number, as n is a big number, so the square root of the ratio is something like 100, and you can do arbitrary 100-bit computation. I mean, the computer scientists here realize that 100-bit computation, arbitrary 100-bit computation, is a lot of mental computation, much more than I believe any one of us can do. Okay, so if you are, if you want to have a system that has no obvious limits, upper limits, or that are limiting. So you are safe with this number, with these numbers. Okay. What I want to show you, what I want what I want to emphasize is the model that I showed you is something that we simulate. Okay, this is our model, and we simulate it. Okay, this is how we do our work, and it is software implemented neuromorphic computation. I mean, I don't know if any of you are interested in neuromorphic computation, but I mean, this is a competition. Okay, this is software implemented neuromorphic computation. To simulate T steps of the model, T, well, one of these steps where every step is a spike of some spike in neurons. One is computer time, which is proportional, and the number of areas is hidden in the notation. So it's, maybe it's a few dozen times more than that. T, the small number, like 10 to the minus 3 times n squared. Okay, that's huge. That's n to the 14 or something. That's 10 to the 14 or something times t. Okay, where t is the number of seconds times 20, because we assume that this works at about 50 hertz as a gamma oscillation. This is very daunting. Okay, so we wouldn't know how to do that, but we have found a clever algorithm to do it. It's something called lazy simulation in computer science. Essentially says, if a neuron has not spiked so far, ignore it, pretend it doesn't exist, okay? And introduce it when it first spikes, okay? A lazy simulation technique reduces this to pk squared t squared. So basically, we have traded a factor of t for n squared over k squared, which is huge, okay? And this is our breakthrough. It allows us to simulate a few seconds of brain time at this laptop, okay? And 3 seconds is a very short life for a brain, but 3 seconds allows us to simulate some cognitive phenomena, okay? And this is what I'm going to show you. Is this clear? Yeah.
So with the t squared term, does that mean that like you can't go long?
Yes, exactly. Yeah.
Worse?
Yeah.
But for a short period of time, it peaks.
Yeah. Exactly. Yeah. So t squared eventually will kill us. I mean, we know that. But and then if you want to do something more complicated, then you have to do the following. You have to run it for 3 seconds, and then run it for 3 seconds again, and hope that nothing interacts badly with what happened before. Okay, that's. All right. Okay. This is what I'm going to show you now. Cognitive phenomena. Okay, how you can implement with this model cognitive phenomena. Remember that's our plan. Okay, and we have done a few things here. But what I'm going to show you is language, okay? So, which to me is the most exciting So it's the hardest thing, so this is a cliche. It's the hardest thing that any brain has ever done. And so it must tell us something. I mean, what I mean, here is why I think that language, I know that language is not popular in neuroscience, okay? And let me tell you why I think it's essential, okay? Language is a living fossil of the brain. By all of this, I mean that language didn't exist 3,000 generations ago. And now it exists in 10,000 different forms. And these 10,000 different languages have evolved. Why? How? What was the fitness? Okay, the fitness was sort of that it was, every step was trying to make them more conducive to learning by baby brains. Okay, so and more expensive and everything, expressive and everything, but basically its affinity with the human brain is what led this, and so it is a mirror. It's an amazing mirror of the brain. Okay, and it's dangerous not to study it if you are interested in the brain. And we have known a few things about language for a long time, for 150 years, and now we know an amazing amount more. Okay, because there are some great experiments. I'm going to show you one of these experiments. That one that actually inspired me a lot. Okay, so I saw a talk about it by chance, and so I captivated my interest immediately. So let me show you what they did. They had hundreds, perhaps thousands of subjects in many languages, and they were hearing recordings of single syllable words in many languages. Spoken at 4 hertz, the same speed I'm talking about now, but more rhythmic. And then what they did, they took all the data, the MEG. They took all the MEG data, and what they did is they took the Fourier transform, and guess what? There was a peak at 4 hertz. Because obviously 4 times every second, the brain had to fetch this word and see if it knew what it means, okay? And then they did something clever. They repeated the experiment, except that every 4 words made sense. Okay? And guess what happened? There are 3 peaks now, okay? There is, of course, the one at 4, but then there is a peak at 1 hertz. Why? Because once every second, the brain created a sentence. So this has a different signature, okay? And twice every second, the brain created a phrase, right? I mean, it has a different signature. So what I think happened, essentially, is this, okay? That the brain was creating trees as it was hearing this, okay? I mean, there is no, the authors argue, actually, that there is no other rational explanation. They have they have several side experiments to rule out the alternative explanation, and which is amazing, okay? Because we have trees in our brain. You create right now trees in your brain, and you create these trees at 4 hertz. Okay, in other words, you create every 12 spikes in your brain. You create a new node of the tree. All right? How is this done? Okay. And here is what we got out of this. I mean, can you simulate parsing? This is something I've been working for a long time. Okay. And finally, what I'm going to tell you now is we did implement a parser of English that is implemented by spiking neurons. Okay. It's implemented in our model. Okay? There are since when I was a graduate student, they were very clumsy parsers of English, okay? In the 1990s, you started to have more sophisticated parsers of English. Now you have incredible parsers of English, okay? This is one of the worst ever, okay? That I'm going to show you. Its only advantage is that it is implemented by neurons, okay? That it's implemented in a biologically plausible manner. So here is the architecture. You have, these are brain areas. There is a particularly special brain area called the lexicon, where you have all the words you know. There are fibers connecting this and these areas. These areas are suggestively labeled by syntactic roles. And let's see. And these, what we have done in the parser and subsequent work is we try to make it compatible with the consensus in neurolinguistics. Okay, there are a few subjects on which neurolinguists have a consensus. For example, that there is a lexicon. Okay, and that there is a place where words find their syntactic role in Wernicke's area. So several other things. Okay, about how semantics are represented, and we're trying our work to be consistent with any place where neurolinguists have a consensus. Okay, the parser is a sequence. So we assume that phonetics has been solved. Here's what I mean. Your brain, when you hear me speak, does an incredible fit in the beginning, that it takes my sound waves, makes them, so finds the word boundaries, makes them into words, and then finds the appropriate place in lex. We basically we telescope this loop. Okay, we say that basically what we have is a sequence of excitations of words in lex. Okay, this is our assumption. All right, because this is phonetics is an amazing miracle. 3-month-old babies know how to find word boundaries. Nobody knows how this happens. Okay, so it's a problem that computers have had until recently problem solving. So each word assembly, each assembly in the lex, besides its representation, has an action set. It is inhibit actions implemented by long-range interneurons. And the action set of every word implements and reflects the word's part of speech. Okay, nouns have a different action set than transitive verbs, different action set than intransitive verbs. And when the word assembly fires, its action set is executed. And if you think about it, if you are looking for a word to call the sum total of all action sets in the lexicon, I know of no better word than grammar. Okay, this is the grammar of the language. Okay, the action sets. A bunch of long-range interneurons. Suppose that the input is cats chase dogs. Okay, we start like this, the initial state. Why is this the initial state of the machine? It is the initial state because this is English, and we know that we are likely to hear the subject before the object, and therefore the first noun I know we want to project it to subject. Okay, if this was German or Arabic, German is loose, Arabic is verb first. German is flexible. So you can have the verb or object first. Then we will be starting a different state. So German babies have a different start state of a parser. So when cats is heard, then basically it is projected to the subject area because that was the available fiber, and then the fiber is inhibited again. Then the part of action set of cats is to open these two fibers, to connect to the verb area, because the verb is being expected now. Then when chase comes, it is projected, and then because chase knows that it is a transitive verb, it opens up a fiber to the object because an object is expected now. when if it was cats run, it would not happen, okay, because run is not a transitive verb. Then dogs comes, and it is connected to, it is projected, and we are done, okay. Now, you are right to be a little disbelieving. I mean, how do we know that the sentence was parsed correctly, right? Okay, and here is how. After this input, high synaptic weights form a valid dependency tree. So there are some side effects of this processing, which can be recovered and convince us that we have a valid dependency tree of that really this was the structure of the sentence so the dependency tree is how NLP folks and sort of statistical linguists like to treat sentences. There is the Chomskyan, so the universal grammar way, a valid parse tree. And it turns out that our system constructs also a basic valid parse tree. By this I mean the parse tree of the main constituents of the sentence. I mean, if you have a long sentence like certain appropriately trained cats very often chase even the world's fiercest dogs, we would create only the parse tree for this tree for the top three words. Okay. So if you look at it as neuromorphic computation, it's implemented exclusively with spikes of stylized neurons. Okay, there is nothing more is at work, we need maybe in excess of several tens of millions of neurons and trillions of synapses. Okay, so this is more than the best, the most advanced neuromorphic chips can do. It parses sentences like this. The young couple in the next house saw the old white car of the main subject quite clearly, suspect quite clearly. Its speed is roughly the speed I'm speaking now. We also have running parsers of Russian, Japanese, Hungarian, Chinese, and there is no reason to stop there. The code is available online. Okay, you can play with the parser. Incidentally, yeah.
You mentioned in the sort of you have all the fibers connecting to the different parts of speech. That in different languages you kind of have to reorder this. So in these different frameworks, is there a way to kind of combine that, or do you have to? Yeah.
So I'm going to talk about my last subject is language acquisition. How this So I'm going to this is a wonderful question. It has been bugging us for a long time, and now we're facing it. Okay. Yeah. So the question is, how do you get this? Okay, how do you get this mature language organ? Yeah.
Yeah. So this is really exciting. So as soon as I how to understand what subject and what's object and what's verb, it depends on the temporal order of the word, right? And then there must be, so when you show the diagram of like the synaptic connections connecting to each other, but then there must be an arrow probably drawn by synaptic potentiation depression or something. But then if you think about the bilingual person, then maybe the order of the subject and the subject and the order object can be switched. Then how do you change that that directionality?
Yeah. So bilinguality is not a problem. I mean, we can, I don't know how to model. So bilinguality is not a problem. We can host in the same lexicon in the same both English and Spanish or English and Arabic. So so it's not we can do this, and probably it will become clear as I go on. Okay, but yes, I mean, Arabic babies who learn Arabic, they will put the verb first, and yes, I mean, this we know how to do this. But a great question. The real challenge is that we have to do it in a way that is not specific to English. Okay, so so I mean, when I say Chinese, it's Mandarin. I don't know. Yes.
So you have like, let's say, I do not know how many neurons our brain has, but to me, your model needs lots of neurons to solve one of the million tasks that the real brain.
Yeah. So believe me, it was worth it. Yeah. It's not. We're not wasting any neurons to language. Don't worry. Yeah. I mean, our brain. So I think maybe no other mammal has enough neurons, sort of, to host the same. But I mean, but we have so many more neurons than others. Okay, so
Science question also. Why do we need these long-range inhibitions? Usually when we talk about projections, they're exactly
okay, because you want to know where to project, and more importantly, where not to project. Okay, you want to protect the areas, so that are while you are doing your projections, you want to protect the other areas. Okay, when you are projecting to the subject, you want the verb to not notice. Okay, this is how it's done. Okay, we are finding more ways to do it. Okay, so different ways to do it, and this is a place where there is no consensus. Neurolinguists don't agree.
But do we know something that actually in language areas there are more of these long-range inhibitory neurons?
I mean, frankly, long-range inhibitory neurons is something that I and Pusaki like, and we have observed in the hippocampus. Okay, so I'm not sure that this is what it is. Anything that works like this would be enough for us to do language. Okay, so we call them long-range interneurons, tongue in cheek. Okay, so that whatever the brain has that can do this work. Okay, can protect areas from inadvertent
Do
project.
I understand this correctly? That this is just this sign change in your model? Like you can just replace that with
Yes, exactly. Yeah. So anything that has this behavior. Okay, so it will do. And I mean, I told you that Peter Dayan believes that it must be some kind of thalamocortical loops that do that. Yeah. Good. So here is something. How much time do we have? -5 minutes.
Maybe 10 minutes.
Okay, cool. Okay. So I'm going to skip most of this, but I mean, I mentioned Chomsky and mentioned statistical linguists, or empirical linguists. So one of the Chomsky schools, or one of their preoccupations was recursion. Okay, so that sentences can embed sentences, can embed sentences, can embed sentences. Okay, and how does the brain do that? And I mean, here is I said the young couple in the next house was fine. Okay, but the young couple who live in the next house would crash our compiler because say what? A second verb, live. What is this? Abort. Okay, so. But obviously this is a fine sentence. Okay, so we worked hard and we found out how to do this. And so one thing, if there are any language theorists in the audience that I want to tell you about this experience, is that in order to do this, we had to introduce context-free languages. Okay, so in other words, we had to introduce the whole of context-free languages in a way that sort of justifies Chomsky for coming up with this rather both restricted and overly general notation for language in the 1950s, like 50 years, 70 years ago. In any event, you know. So, for example, how do you parse this? And we have. I'm going to. Anybody has photographic memory will know what I'm talking here. But I mean, I'll be happy to talk to you afterwards. Okay. All right. So let me tell you. Okay, you asked some wonderful questions about parser. Let me tell you some ones that we didn't ask. But now we have parsers that can do so much more. Okay, so you know we have BERT, for God's sake. Okay, why are we showing this parser? Okay, I think I answered this, but I'm telling you again. True, but ours is biologically plausible, implemented exclusively through the spiking of stylized neurons, and you see no fundamental. You know that's important. We see no fundamental limits to how good it can make it. Okay, by working harder, by introducing more features, and so on. Okay, you know, so I don't see that we cannot capture all of language this way. Okay, you know, that's my point. So, but how are you going to test your theory in humans? Okay, that's a great question. That's not a theory, but I don't know. It's not. You know, I'm not. You know, it is a proof of concept. Okay, so you know, in other words, I'm trying to convince you that language does not require divine intervention. Okay, that from the neurons that we know, you can, you know, abstracted of course and all that, so you know, can have language. Okay, this is what I'm trying. Okay, so it's not a theory. I'm not opining that this is how the brain does parsing, even though I would love to be so lucky that the brain does parsing exactly the same way, in which case I have some predictions also. Okay, so you know, but I don't think they're very interesting predictions. Okay. The question that was asked before, okay, how does this complicated mechanism come about? Okay, so you know that a baby is born in England, a baby is born in Japan. Okay, how can the same brain sort of, you know, learn these two different languages? Okay, how do you? Okay, and this is what we have been thinking about recently. Okay, so I mean, this is a question. I mean, that's sort of very interesting. That a bold experiment. You know, most of you are experimentalists, so you know that a bold experiment entitles you to ask new questions, or you know, an askable question. You know, I don't think that this was considered a question that we should ask. Okay, somebody can ask, what is the neural base of language? Can this be the neural base of language? And the answer is no, really not. And because the hard, you know, because the hard part is filling the blanks. Okay, so the question is, how do you do this? How do you learn the words and their meanings, which we have talked about? How do you learn the syntax? How do you learn the names of these areas? Okay, the role of these areas. How do you do all this? Okay, and that's my granddaughter, by the way. And how about semantics and generation? Okay, you know, the opposite. So what makes us generate language? What I'm doing now. Okay. The neural base of language, I think, is something like this. In other words, a bunch of areas, synaptic connections, many millions of, you know, hundreds of millions of neurons, plus hardware for semantics and generation, different hardware that does semantics, different hardware that does generation, plus the ability to learn all these things. Okay, so you know, basically it must start from a neural tabula rasa and learn this. Okay, so basically what we are doing now is biologically plausible language acquisition. What are we trying to do? Hardware is a tabula rasa of a couple of dozen brain areas, fibers, and populations of long-range interneurons. Input is a modest amount of grounded shared attention language. By this I mean the following: that the learner, the baby, is exposed to language. Okay, it does not have to be a dedicated mother who knows what she's doing. Okay, but is exposed to language which is grounded, happens in the world, okay, in the presence of objects in the world and actions in the world, and this shared attention that the learner knows what the tutor is looking at and has their attention at. Okay, so this is the only thing, and the output is a mature language organ with representations of syntax and semantics, a parser, and a generator. Okay, so this is what we're working on. And I mean, as I was telling the people I talked to before, it's a little scary that I don't see the sort of, I don't see an obstacle. Okay, I'm pretty sure that within a few months we are going to have something. Okay, so this thing for a language that has, I don't know, maybe 100 or 2 words. Okay, so let me tell you where we are. We have as with the parser, assume that phonetics has been solved. Okay, so we only talk from the symbol. We can implement learning of nouns. We know how representation of noun semantics. You see, when you do parser, you don't have to worry about semantics. Okay, but here semantics is the front. Representation of noun semantics, a representation of verbs and their semantics. Learn how to generate 2-word sentences like "daddy left," which is the first syntactic thing that babies do. Learning the word order of the language, and we have 2 alternative ways to do that because we are undecided. And we are solving the hard case, which is learning syntactic rows of words from overhead language. In other words, not when this is ball, this is cat, this is runs. Okay, this action is called run. Okay, so because, but I mean, when you hear just sentences, dog jump. I mean, if a baby hears dog jump, does not know if and sees dogs jumping. It doesn't know if this is English and dogs is the animal, or this is Arabic and dogs is the verb. Okay, and it turns out that by presenting a few dozen such sentences, when you have half a dozen verbs and half a dozen nouns, you can actually our model can learn this. Okay, can figure out the syntactic role of the words. Let me quickly tell you how semantics are represented. Okay, dog is a sort of a concrete object, so it has a phonetics root, so which I'm not talking about. It's rooted hardly, very forcefully here, but it's also rooted forcefully to vision. Okay, because concrete things are rooted in vision. Okay, concrete nouns. It may have some connections with motor. So these are all peripheral semantic areas. Okay, they are close to the corresponding. So vision is very close to the visual cortex. Okay, to the inferotemporal cortex. And we know this from fMRI samples. Maybe it has an auditory signature. Maybe it has an emotional signature. I love dogs. I'm afraid of dogs. Okay, but so all these things define the semantics of the word dog for this human. Okay. Verb is very so there is okay. So it implements the widely accepted hub and spoke semantics theory in neurolinguistics. In other words, that's really how neurolinguists think that indeed the word is a star of representations. Okay, the symbol and the various aspects of its meaning. And in some sense, I mean, that's not unlike what in AI we call word to vec, okay? Because this is every word is a large vector that represents the word. now the assemblies, their overlap and the strengths of their connections are dynamic, okay? In other words, that how two words overlap as symbols, or they overlap elsewhere. Okay, I have a similar problem as before. Okay, that's okay. Are dynamic. Okay, in other words, they can change. Okay, that the details of the representation, including the strengths of the connections, can change dynamically, reflecting experience. Okay, in other words, the semantics of the words in your lexicon change every day. Okay, so many words change slightly their meaning after my talk. Okay, things like man is to woman as king is to what is answered automatically. Like Word2Vec can do that, but we need an algorithm. Here you don't even know. Just by saying to somebody, a man is to woman as king is to what? Okay, queen comes to their mind. Okay, the word queen comes to their mind in our model. Okay, so and that's something we have implemented. I saw the tree with my binoculars will be disambiguated correctly. I saw the tree using my binoculars, not that I saw a tree where my binoculars are hanging, okay? And the reason is that seeing binoculars have more semantic context overlap, and therefore the synaptic flow between them will be more stronger, and the thing will be assigned to the right. And of course, you could be wrong, okay? No matter what. So, all right. To conclude, as Max was very kind to say, I've been in the beginning. I have ventured in many fields, trying to solve their problems, and in my career, but nothing has been as incredibly bottomlessly steep, okay, as the brain, and as difficult, but also as rewarding. So as I said before, I don't think that I think neuroscientists have been ignoring language at their own risk, because the language hides a lot of information about our brain. And one of the most gratifying things that our work with language implementation in the brain has given us is our sort of right to ask questions that have not been asked before, okay, because they were considered like blasphemous. So we have made progress in biologically plausible acquisition. So is this a promising way forward for in AI? Okay, that's a small part of the audience is interested in the question. I think so, but really, what interests us all is this approach sort of the right way to go about finding access logic? Okay, so these are my collaborators. Max is, Daniel Tropolsky is also a graduate student at Columbia, and Mike Orins is a linguist, NLP researcher at Google. Thank you very much.